Have you ever been told this silly lie? Math is never going to be used in real life. Well, you're about to prove all those people wrong in just a few minutes by sticking around because we're going to use balloons, believe it or not. So say we're inflating balloons for our awesome new karate dojo, and the rate at which the balloon grows is represented by the equation you see here. Note, this is f prime of t, not f of t. It's a derivative equation. And so we're going to let t be the unit of seconds here. And f prime of t, we're going to say it's going to be representing the volume rate of change of our balloon in cubic centimeters per second. And when I graph this here, remember that because we're dealing with the derivative equation, f prime of t, what does that tell us? It means that at any point in time t, if this curve is above the t-axis, the balloon is growing in size because the rate of change is greater than 0. Similarly, after this point here, from then on, we will see that the balloon is shrinking. So for our dojo, instead of just guessing and wasting our time inflating a bunch of balloons and popping them and almost giving up, we can actually use math here to prove and to know exactly how long to inflate the balloon for, to also then figure out what the final size will be. Because remember, we want to have this dojo be the best dojo in town and the balloons to be as large as possible. So all the students across the street will come over and they'll be like, yeah, let's join Number Ninja Dave's dojo. Okay, so what do we do here? Well, there are 2 points of interest here, right? T equals 0 and this other point, well, we got to figure out what that value of t is. Because what does that mean? Well, the rate of change has something going on where we're going from increasing the size of the balloon to decreasing. Now, t equals 0 is a silly answer here because we haven't even inflated the balloon, but it's still good to look at. So we know that t equals 0 here is not going to be one of our answers. But this point here, we got to figure out what value of t lands us there. And what we want to do now is to figure out that point. We're going to set that derivative equation I gave you equal to 0, right? Because that tells us that up until that point, we stayed above the t-axis. So the balloon was growing and growing as we were inflating it. And at this point t that we want to solve for, moving forward, it's only going to shrink. So we want to stop right there. And so what I can do now is I can just simply divide both sides by t squared, giving this new equation. And the reason why that's okay, I don't have to divide by 0, because I already told you t equals 0 is not going to be our solution. So that's safe to do. And now when I solve this equation for t, we'll find that 1/10 t equals 10. And that's going to result in telling us that t means, okay, we need to inflate this balloon for 100 seconds. But we're not done, right? Because that's just step 1 of the equation being solved. And step 2 now is, what's the final volume going to be for that balloon to be as large as possible? And before I tell you that and move on, if you haven't already and you like this video and you want more tips, be sure to ninja kick that subscribe button. Okay, so to get the final size of the balloon, remember, when you're given a derivative function here, we need to look at the area under the curve from t equals 0 now to t equals 100. Because we got to stitch all those rates at which we are inflating the balloon at any given point in time all together to figure out the final change in volume of the balloon starting at time equals 0 to time equals 100. So many of you have already seen this, but this becomes a definite integral problem where now we're going to integrate that derivative function I gave you from t equals 0 to t equals 100. And this is straightforward, right? Because we have a difference of 2 polynomials here. So if you remember, it's no different than integrating each part separately. And that's going to give us an integral that's going to be 10 over 3 t cubed minus 1 over 40 t to the 4th, all evaluated from the limits of integration from 0 to 100. Now, the lower limit of integration, 0, is pretty simple, right? Because we already know when you plug it in everywhere for t, you'll get 0 here on the right. And then on the left-hand side, this becomes a rather large number. But when you solve this, you get an approximation for what our awesome balloon size is going to be.